I just want to make sure that we're prepared for it and we understand what's going to be on the exam and that we're comfortable with a lot of this stuff. It really helps. I'm going to start going over this material tonight, and I'm going to do another session online at 9 o'clock on Wednesday and a session on Saturday at 10 a.m. So you guys are welcome to tune into that. It's not required, so it's completely voluntary. You can join anytime you want. You can leave anytime you want. You don't have to announce that you're joining or leaving or anything like that. It helps me a lot if I know what you're having an issue with, so I can direct it a little bit more. Even, 3 sessions sounds like it might be a lot, but it's really only a few hours of time. What's that? 9 p.m. It's on Blackboard. There's an announcement on Blackboard with links for Wednesday and Saturday. It sounds like, like a lot of time, 3 sessions, but it's really only a few hours, really, realistically. So it really helps if I know what you're uncomfortable with and what you think you might have problems with. Because basically, I kind of went back through the syllabus and I listed the materials that we've covered since the exam 1. Remember exam 1 where you covered binomial distribution, we covered variable types, we covered a lot of the material like that, probability, for instance. But after exam 1, we got into the standard normal distribution. We learned about the empirical formula. You remember that was the 64, 95, 99.7% of the normal distribution based on the z-scores, or based on number of standard deviations. We learned about standard deviation. We learned how to calculate the z-scores. We learned how to add the number of standard deviations from the mean. We learned how to use the z-table, and we learned how to use Excel to find the z-table and to find areas on the normal distribution beyond that simple 64, 95, 99. Okay, then we went on. So that was for the standard normal distribution, the distribution of populations. We don't really run into that much, but it's one of the things you might see a problem on. From that point, we took a look at the distribution of sample means. If you took from a population, repeated sample means from that population of a certain sample size, what the distribution of those sample means would look like. And that we found would have a normal distribution also, just like if the population was normally distributed. In fact, we would probably have a relatively normal distribution even if the original population wasn't a perfect normal distribution, right? So that might come up, something like question like, can you does the population have to be a perfect normal distribution for you to use the assumptions that we make with the sample distribution? Okay, and let's see. We calculated different kind of point estimates. In other words, means and proportions, depending on the kind of data it was. If it was binomial data, we calculated a proportion, yes and no, diabetic, not diabetic. If it's a numerical variable, we calculated a mean. And once we calculated a mean based on the sample, we wanted to know how certain we were that we were close to the mean. So since we're taking a sample, we never know based on a sample what exactly the mean is for the population. So we have to have some information about how reliable that calculation is and what range we would expect the true mean to fall within. So to do that, we calculated based on the standard deviation, the sample size, we calculated a standard error, a standard deviation basically for the sample means, which we call the standard error. Okay, and using that, we calculated confidence intervals. So you guys recall that, right? We went through that whole thing about a 95% confidence interval. We used a z-score of 1.96, so on and so forth. Is that showing up there? Yeah, I guess it is. Okay. You guys were looking over my shoulder. I want to make sure you have that. Now, this is on Blackboard. If you need this, this is on Lab Section in Blackboard right now. So you can go back and look at it. So if you want, you can also write it down or take pictures of it as well. So sample distributions, different than the normal population, the standard normal distribution, the distribution of populations. We looked at standard deviation. When we worked with sample means, we looked at standard error. the standard deviation of the population divided by the square root of the sample size. Okay, so now once we got into that, we started to use that information to test certain hypotheses. For instance, whether we could tell the mean of one distribution was mean of one population was different than the mean of a second population. So in order to test that theory, we set up a hypothesis. For instance, the mean of population 1 is equal to the mean of population 2. And we tried to gather enough evidence to be able to reject that null hypothesis and accept an alternative hypothesis, which was usually that the two means of the two populations are not the same. Okay, so now there's probability involved in this because, again, we only know the sample means that we've taken. We don't know what the true population means for those two populations to be able to say that they're different. So we have to calculate a probability that we would get an outcome that would fool us, a probability that we'd be wrong if we rejected the null hypothesis. Okay, and that was we call that P. And we wanted that P value, that significance or P value, to be less than a value that we set as the maximum amount of error that we would tolerate. Okay, and usually we set that at 5%. We call that alpha error or type 1 error. We set that at 5%. So we're going to take a look at calculating that P value and that hypothesis for point values. Now, when we're dealing with two populations or two samples, what kind of tests do we do with two samples? Test the P value or test the two, right? Two, we use the t-test, right? Okay. If we're dealing with, in other words, if I'm calculating whether the proportion of Americans that are diabetic is the same as the proportion of Canadians is diabetic, I'm randomly sampling Americans, randomly sampling Canadians, and then I'm comparing the two proportions, sample proportions that I get. That I'm going to use the t-test for. Similarly, if I want the average weight of Americans, average weight of Canadians, that's a numerical variable, but I still use a t-test. Okay, that's for two values for those variables. Okay, if I want to compare more than two values for those variables, okay, for instance, if I want to know whether different ethnicities, if there are different rates of diabetes for different ethnicities, I might calculate a proportion for African Americans, for whites, for Hispanics, for Asian Pacific Islanders, and so on and so forth. I'd have multiple possible groups that I would be taking that value for. So instead of comparing two proportions, I could be comparing 3 or 4 or 5 or 6 proportions. For that, what test would I use? ANOVA, analysis of variance, right? Because basically it gives you an opportunity to compare many values, categorical values, in terms of a point estimate. Proportion could be one, and also could be the means for, let's say, the average number of sugary drinks that each one of those ethnic groups drinks each day. So we can have when we want to deal with analysis of variance. So analysis of variance, if we set up a hypothesis for analysis of variance, the generally hypothesis is that the means are all equal. mu1 equals mu2, mu3, right? Notice I say mu, not the x bar, because it's really the populations we're interested in. The alternative hypothesis would be that they're not all equal, right? At least one of them is, at least two of them are different from one another. When we complete the analysis of variance, we may know now that we can reject the null hypothesis, but it hasn't told us yet what the which of the means are different from one another. And you guys remember what we did in order to determine which specific means are different from one another? We ran post-hoc tests, right? So we're going to take a look at that as well. So it's likely something like that may be on the test, right? So we have normal distribution, basic stuff, sample distribution, and standard error, calculating that. Based on that, we could have questions about confidence intervals. And from that, we could have t-tests, comparing two means. And then we could have analysis of variance, comparing three or more means at the same time. And so that's so far, we've dealt with either binomial variables or we've dealt with means, numerical variables as well. So now, what about if we have two variables that are both categorical? For instance, if we want to look at a situation where there may be certain, say, an exposure, like a person was either exposed to asbestos or not exposed to asbestos, and the outcome might be that some people that were exposed or not exposed might develop lung cancer, for instance. Okay, so now we have, for each individual, we have two categorical variables. Were they exposed? Yes or no, that's categorical variable. And the outcome might be, did they get lung cancer? Yes or no. Okay, so how would we organize that data typically, where we have two categorical variables? What are those tables called again? Contingency tables or crosstabs, right? Okay, now I think we did, remind me, did we do a diagnostic test before the first exam? We did, right? Yeah. That was that was like week 3 or something like that. Yeah, so it's unlikely that's going to be on there, but we're going to look at contingency tables because you may have situations like that, an exposure and an outcome. Now, it's not always a 2x2 table the way it is with a diagnostic test. Okay, we could have, for instance, different levels of exposure, like no exposure to asbestos, a minor exposure to asbestos, a major exposure to asbestos, an extreme exposure to asbestos, and then 2 columns with lung cancer and no lung cancer. So we'd have a 4x2 table or a 2x4 table and so on, right? But the key is they're both categorical variables. So we really can't analyze them the way we would analyze numerical variables. In other words, using a mean, for instance. Okay, but we can analyze them by analyzing whether that table takes the proportions that we would expect it to take. The values that we see in that table that we create are there at the same rates for all of the exposures. In other words, are people that had no exposure to asbestos, are they getting cancer at the same rates as people that had an extreme exposure to asbestos? So we can look at that and we can develop from that first table, we can develop another table that's called anybody remember what kind of table the other one was? Our first table is the values we observed, right? Observed values. Our second table is our expected values, right? And we can calculate that table. A lot of times we use SPSS to do that. We could do it manually if we wanted to, but we'll take a look at that. I don't think they'll force you to do it manually, but we'll take a quick look at how we might do it if we are asked to do that. Okay, so chi-square is the statistic we might use there, right? And what would a hypothesis test look like for chi-square? Chi-square would be, for instance, the null hypothesis would be that they're independent, or that there's no association between the two variables, between asbestos exposure and lung cancer. You could call it they're independent, or you could say that there's no association. The alternative hypothesis is that they're not independent, or that there is an association. And how do we prove that? Well, we calculate that chi-square value, and from that chi-square value, we calculate a probability that we would get that big a difference between the observed values and the expected values that would only occur less than 5% of the time by chance, rather than by really there being a difference between the expected and the observed values. Okay, now the other nice thing is that we have a 2x2 table. We can run some special tests, which really kind of give us a bit more information about the exposure and the outcome. And you guys remember what those tests were? If it's a 2x2 table, besides chi-square? Yeah, odds ratio and relative risk. Okay, so now in order to compare odds ratio and relative risk, we might calculate the odds of a person that's exposed to asbestos getting cancer and the odds of someone that's not exposed to asbestos getting cancer, and we would put one over the other and call it the odds ratio. Right now, if there's no association, we would expect that the odds ratio is going to be equal to 1. And how do we know that we have enough evidence that it's different than 1? What do we have to know besides that? we have to know the confidence interval for the odds ratio. And if the confidence interval for the odds ratio doesn't include the number 1 in that range, then we know that there's less than 5% chance that we would be wrong if we reject the null hypothesis that there's no association. So the odds ratio gives us some extra information too. It gives us a relative idea of how much bigger the risk is from exposure to asbestos, not just whether or not we can say that that there's an association or not. Okay, so the odds ratio is interesting for us as well. So once we get through that, we get through odds ratio, then we got into correlation, linear regression, multiple regression, which we've just been poking at right now. Okay, so now, how many of you guys are actually going to wind up doing some form of regression for the project? Is that something that's required for everything? What's it? I'm sorry.
She asked that we include a logistic
Okay,
regression.
well, but I mean, did she? I would imagine that would have something to do with which variables you chose, right? Okay, all right. I have to take a look at the actual instructions and stuff like that. So yeah, so as far as regression is concerned, correlation and regression, we as we talked about that, it allows us to see what the association is between one variable and another variable, but it also allows us to quantify it. Like, in other words, if we have a certain increase in one variable, how does that impact the value of the other variable for most people in the study? Okay, so we can take a look at that as well. Okay, so I'm thinking we'll get started right at the beginning and work our way through this. And I'm thinking that we'll go through this from the start here. I'm hoping maybe we'll get to. Oh, it's already almost 8 o'clock. I'm hoping that. What's that?
We already did the standard formula on the last one.
Did we? I don't know about that. Did we? Empirical formula. Okay. Z-scores. Did we do Z-scores tables? Okay, so we'll go straight to standard error. Well, I just want to introduce that in terms of calculating Z-scores using Excel, but and then I'll skip on to that. But I'm hoping to get through maybe at least start on some chi-square stuff tonight, and then we'll pick up from chi-square and correlation on Wednesday night, and I'll publish that also. So if you can't join us at that point, and then I'm hoping that what that'll mean is that we can leave Sunday for questions. Like, in other words, if you tell me specifically, how do I solve this problem or something like that. If you email me in advance, it makes it a hell of a lot easier for me to, be prepared to answer the questions and stuff like that. So, or if you have specific areas that you have issues with. So hopefully we'll get through all of this in some form of review by Wednesday night, finish it up by Wednesday night, and then have Sunday to actually answer like specific questions and stuff like that. Okay, so there's a document I put up, which is kind of a quick kind of example table or maybe practice document for the exam. Okay, and yeah, let me blow this up a bit. Okay, it's on Blackboard. Okay, I'm going to skip past that first question and go to problem 4. 2003, the American Psychiatric Association conducted a survey of psychologists of 81 psychologists who received master's degrees in 2003. The mean income was $43,000 with a standard deviation of $16,870. Construct a 95% confidence interval for this population. Okay, so I'm gonna do that manually now. Okay, and I'm gonna try not to kill too much time on simpler stuff. Okay. Okay, so the X bar, right? We don't know the population standard deviation. X bar is equal to 43,500. Standard deviation is equal to 16,870. Okay, so we know in order to calculate a confidence interval, we have to know the mean, the point value, and we have to know the distribution of the sample means that I would expect from this population. And in order to know that, I have to calculate standard error. Standard error is equal to sigma over the square root of the sample size. Now, do we know sigma? Yeah, we kind of know sigma, right? We know the standard deviation of the sample, right? We don't know the standard deviation of the population. So that confines us a little bit to wondering whether or not we have a big enough sample size to reliably say we are close enough to the standard deviation of the population. So instead of calculating a z-score, we're actually calculating a t-score because we don't know the population standard deviation. Now, when that sample size becomes very large, it's typical for, especially the first time you run through these analyses, to say, well, I'll just ignore the fact that it's a t-score and just calculate a z-score instead. Okay, so let's see how I would do this. So my confidence interval is going to be equal to x bar plus or minus the standard error times, the one for 95% confidence interval. If it's a z-score, it would be 1.95 times, actually 98 times 96, excuse me, times what? Yeah, good idea. Yeah, t-score. Okay, well, t-score or z-score. We're going to talk about that in a second. X bar plus or minus 1.96. Why did I pick out 1.96? 95%, right? That's our empirical rule, 95%. I may not stick with that. It's going to depend on the sample size, right? If I decide I have to use the t-values because I have a small sample size, then that might change that number. Okay, if I decide I can use the z-score, it's going to stay 1.96. 1.96 times the standard error. Okay, so what's my standard error equal to? For this, it's equal to, what was my standard deviation? 16,870 over the square root of the sample size, which was 81. Square root of 81. Okay, that's 9, right? Okay, so let's work that out. 16,870 divided by 9. Did I do something wrong here? Okay. Whenever you guys chatter in the background, I suspect I did something. I'm going to call that 1875. Okay, that's 1875. Is the sample size at 81 a big sample size? Yeah, pretty much, right? Once you get over 30, right, you consider a pretty sample size. So I'm going to stick with that 1.96. If I decided that it wasn't a big enough sample size, what number would I have used instead of 1.96? Well, I would have gone to the t-table. Okay. Okay, why can't I find it now? Usually it pops right up. Let's try it this way. There we go. Okay, I would have gone to the t-table. I would have looked up the number of degrees of freedom, which is 81 minus 1, so it'd be 80, right? And I would go over to a confidence interval for 95% for each tail having 2.5%. So I would go down this middle column down to 80, and I would have used 1.99. So one of the reasons we're not using 1.99 is just simply because it's so close to 1.96. But if I wanted to be perfectly accurate, I would have used 1.99. Now, SPSS always uses the t-score instead of, even if that sample size was 14,000, it would still calculate the t-score. It might be 1.96001 or something like that. It would still use it. So you can always use the t-score and be accurate. But you kind of like, sticking your neck out a little bit anytime you use the t-score. But for this big a sample size, I think we're okay. So it's one x bar, right, plus or minus 1.96 times 1875. Do I hear an echo? Do I need to? Hang on a second here. Let me mute all these attendees here. Okay, so as I was saying, it was 1.96. 1.96 times 1875. You know where I got the 18? We got both of those, right? Okay, good. Let's calculate that. 1875 times 1.96 is equal to that. I'm going to put that into memory. I'm going to clear this. Okay, so I'm going to add and subtract that from my mean. My mean again was 43,500. Right, minus that value. So the lower end of my 95% confidence interval is 39,826. And the upper part of my confidence interval is going to be, what was it again? 43,500 plus. Okay, you guys remember what that value was called? That 1.96 times 1875, that was called. What was that? It was the margin of error, right? Which makes sense, right? We're adding and subtracting, so it means margin of error. So that's 47,174. And so that's our 95% confidence interval. Okay, so what assumption can you make about the shape of the population in calculating the confidence interval? Well, we're hoping that it's approximately normal. Okay, if your assumption about the shape of the population distribution is not valid, does that invalidate these results? It really kind of depends on how bad it is, how not normally distributed it is. But the standard, our calculation of the confidence interval is pretty robust, so that we can tolerate a certain amount of deviation from a perfect normal distribution in the population. So just because the population is not perfectly normally distributed doesn't invalidate our results necessarily. Okay, so somebody might ask about that on a test. So, okay, so now let's take a look. I'm going to go back and do the same thing now with a point, with a proportion. Time magazine polled in 1,000 Americans. 4% said that they were vegetarian. Construct a 95% confidence interval for the true population proportion of vegetarians. Okay, so very much like we did before. We're gonna, let's see if I can't find my notepad again. Oh, oops. I don't want that. Okay, get a fresh page. Okay, we're going to set up the same kind of relationship again. Okay, we're going to calculate we're going to calculate a proportion of Americans. What's the proportion of Americans that were that they said our p cap for the sample is equal to 4%, 0.04. And what was our sample size? Was it 2,000 or 1,000? 1,000. Okay. Oh, what was it, the year 2000? Is that what I'm thinking of? Okay. Confidence interval. What's our confidence interval going to be then? Our confidence interval is going to be p cap plus or minus 1.96. Now, I didn't hesitate to put 1.96 there, right? Because whenever we're using a proportion, we don't use the t-test. Because part of our assumption for using this calculation is that our sample size is large enough to use the z-values. Okay, so 1.96 plus or minus times the standard error, 1.96 times the standard error. Now, how do we calculate standard error here? Well, first, let's see, we have to know the standard deviation, right? And what is the standard error equal here? It's equal to the square root of p times 1 minus p over n. Okay, that's my standard error here. Okay, so what is my standard error equal to? The square root of You guys remember this formula? Right? Maybe I should put together like a list of formulas or something like that. You know, so yeah. Okay. Yeah. If I miss any, I'll work on it. If I miss any, you guys edit it, add it back, kind of like a wiki or something like that. So what is our PR proportion? Here is 0.04 times, what is 1 minus b? 0.96 over the sample size, which is 1,000. No, the sample size is 1,000, right? Okay, it's 4%. P times 1 minus p divided by the sample size. All of this is under the square root sign. So 0.04. Okay, put memory out here. 0.04 times 0.96 is equal to 0.03. Okay, divided by 1,000 equals that number. That seems like a remarkably small number. But keep in mind, we're working with proportions here. Like 0.01 times 0.01 would be 0.0001, right? But when we find the square root of it, the number which multiplied by itself, it becomes a larger number. So when I go here and find the square root of this number, it actually comes out to be 0.061. It comes out to be about 0.6%. Okay, so 0.006. Standard error is equal to 0.006. Okay, so now p cap plus or minus 1.96 times 0.006. Okay, so this is basically 2 times that, right? So I'm going to speed things up by just doubling it. 1.96 are basically 2 times this would be equal to 0.012, 1.2%. Right, so I'm going to add and subtract 1.2% to my 4%. So my 95% confidence interval for the true proportion of vegetarians in the United States of 2000 is going to be equal to 0.04 plus or minus starters 0.012, which is going to be equal to 0.028, 2.8%, right? Comma, and then added is going to be 0.052%, between 2.8 and 5.2%. Okay. Everybody comfortable with the way I got that? Okay, you can go back over it again. I guess if you play it back and you'll be able to go back over it again. Okay, so 1.96. First I calculated standard error, came out to be 0.006. I multiplied it by 1.96. That gave me my 1.2%. And I added and subtracted that 1.2% from the 4% for the sample, for my estimate, my point estimate of the population proportion. Okay, so if I had asked you at the beginning of this problem, if I had asked you, can you tell me with 95% certainty that there are more than 2% of the American population is vegetarian? With this result, you probably could have said yes. If I had asked you, could you tell me with this result is more than 3% of the American population vegetarian? You wouldn't be able to tell me with 95% certainty, right? Because the 3% is within that range of error. It's entirely possible they could be a little bit less than 3, but they could be as low as 2.8%. You know, I can't say that with better than 95% certainty that they're not 2.8%. So just like before, we're looking for whether the number we're comparing it to is within that range or outside that range. In fact, a lot of times we'll do this test. We won't use a 95% confidence interval, but we'll use a version of this test where we're testing whether or not we can say this value is different enough from this range of values that we think the true mean is. And we would calculate a probability that you would get that big a difference if there wasn't a difference. And we call that a t-test, except that is a single variable t-test, right? Not two variable. We're not comparing two means. We're comparing a value versus what we think the range of means is for that sample. So that's probably a nice logical step for us to take next, is to examine now, instead of proportions instead of calculating confidence interval proportions for means, let's take a look at actually comparing two proportions or two means directly. Okay, and that's what we would do if we were calculating a t-test. Okay, so let's take a look at something that'll give us a t-test. Okay, let's see. Let me see here. Okay, single value t-test. Management claims that the mean income for all senior level assembly line workers in a factory manufacturing MP3 players in Beijing is $350. You know, these problems look familiar to me because I see them like every semester. You know, did we do this specific one before, or is it, I guess not, right? It's me. It's just we have a collection of hundreds of these things, and I can never tell which one. The last time I saw this one. Okay, $350. A concerned client decides to test the claim for a random sample of 9 employees. He randomly samples 9 employees. He wants to know whether or not the true average salary that those employees in that factory are making is equal to $350, is different than $350. Did I say more or less? I just said different, right? So we want to compare whether or not the mean salary for people in that in that population of employees is different than 350. So let's set up a hypothesis test. What would our null hypothesis be? Now this is a single sample test, meaning it's not going to be mu1 is equal to mu2 because we know what one of the values is we want to compare it to, right? So my hypothesis test would be mu salary is equal to $350. That is true. He's right. It is really $350. Now, we want to see if we can't disprove that, whether it's lower or higher. So our alternative hypothesis is mu is not equal to $350. Okay, we could do a one-sided test. We'll talk about that later. For now, we're looking at two-sided tests. So now how would I test this? I would actually do a t-test at this stage. Right, I would actually calculate how far apart these values are likely to be. So there's a couple of ways I could do this. One way is that I could do this calculation, say, in Excel or by hand, right? And the first thing I would want to do is calculate the mean and the standard deviations for the sample that I have, right? And then once I did that, I would want to calculate a standard error for that sample, right? So, and this is a small sample, that standard error is going to be, you know, affected by the sample size. It's going to be equal to, we're going to use t, not the z values, and it is a t-test after all. And we're going to compare that to see how many standard errors apart these two values are. Okay, so now, let's see what we can do with this. Okay, so now I'm going to copy these and paste them into Excel. Okay, how are you guys doing online there? I don't see many comments going on. I see a few of you there, but no comments. You're not in shock, right? You remember this. This wasn't like 4 semesters ago. We talked about this recently. Okay, here we go. Okay, so here are all the values. Okay, is that really 9? Make sure that really over. 2, 3, 4, 5, 6, 7, 8. There's only 8 values. Yeah, it's only 8 values. I'm going to add another one. I'm going to add a 320. Okay, just to make it interesting, so there's really 9 values there. There's a way for me to transpose this vertically, so, but I'm not going to want it. Okay, so the mean, x bar, okay, that's going to be equal to the average of all of these values. Okay, it turns out it's $337. It's less than I would have expected, right? Because if this were true, but this is a sample. We're not sure we have enough evidence to reject that null hypothesis yet. So now I'm going to calculate standard deviation for this sample. And that's going to be equal to standard deviation for this sample of 9 values. And that's equal to 13.94. So now I'm going to calculate the number of, I'm going to calculate standard error now. The standard error is going to be equal to the standard deviation divided by the square root of the sample size. So that's going to be equal to the standard deviation divided by the square root of 9. I'm just going to put 3. Okay, so our standard error is equal to 4.64. So now I want to know whether or not that value of 350 is different enough. Our calculation of $337.78 is different enough from 350 for me to say with 95% certainty, less than 5% chance of being wrong, that that those workers are not paid $350. So I have to calculate now how many standard errors apart that these two values are. So let's see how I would do that. I'm going to say, okay, I want to calculate the t-score, number of standard deviations apart. That's going to be equal to x bar, the value that I calculated, minus the mean that I'm comparing it to, divided by the standard error. Okay, I'm going to put this in parentheses. Okay, hit enter. And I see that my two values are 2.6 standard errors apart. If this were a big sample size, would I reject the null hypothesis? Remember, if they're if they're outside 90% confidence interval, if they're more than 1.96 standard errors apart, I would automatically reject the null hypothesis for a very large sample. That's a z-score, right? But this is a small sample. There's only 9 people in this sample. So how many standard errors apart do they have to be for me to reject the null hypothesis? What do I have to look up? I have to look up the t-table again, right? Okay, so in a situation where I have only 8 degrees of freedom, in other words, only a sample size of 9, our critical value for t that t has to exceed for me to say that there's less than 5% chance that they came from the same population is 2.306, 2.3. Is my value greater than 2.3? It is, right? So even though it's a small sample, I can reject my null hypothesis and accept my alternative hypothesis. If I had failed to reject my null hypothesis, right? If I had, I gave it away. What would be the term if I don't have, if our result was 2.2, we didn't achieve, or that we didn't exceed the critical value, what would I have said about my null and alternative hypothesis? Right? What would I say about the null hypothesis? I can't reject the null hypothesis, or fail to reject the null hypothesis. We don't say we accept the null hypothesis because we don't know if it's true. That's not what we were testing. What we were testing is, do we have the evidence to reject the null hypothesis? So in this case, we can go back to the factory owner and we could say, you cheap son of a, you're underpaying your employees. We're 95% certain, more than 95% certain. Yes. It's equal to x bar, right? Plus or minus. Excuse me. It's x bar minus, it's x bar sample result minus mu, the mean that we're comparing it to, divided by the standard error. We're looking for the number of standard errors, or basically standard error is basically the standard deviation of the repeated samples of the means for sample size 9. So it's x bar minus mu divide. Yeah, we really need some sort of formula sheet. Right? That would have. Okay. So x bar, I didn't think we would really need that. I thought like we would. It's kind of at this stage kind of intuitive. But I've been doing this a few more times than you have, I guess. Yeah, yeah. Okay. Yeah, I have to, every once I have to be reminded that it's like you guys haven't been looking at this for a million years. Okay. You have to look at the table, right? You have to look at the table because the table tells you for your sample size how big the difference has to be between the mean and the mean you calculated for your sample and the mean you're comparing it to, the value you're comparing it to. Is that enough standard deviations, actually standard errors, apart that you can reject the null hypothesis? In this case, it was a sample size of 9, so it needed to be at least 2.3 standard errors apart in order for me to reject the null hypothesis. If this had been a big sample size, like 100 people or something like that, I could have just used the z-score and said they have to be more than 1.96 standard deviations apart to reject the null hypothesis. Now notice, since we're not using the z-score here because small sample size, we can't actually come up with a specific p-value for this probability of being wrong if we reject the null hypothesis. If we SPSS can calculate it, but we don't have all the tables that we need in order to calculate it easily. But we can tell. I'm not going. I was going to bracket the different range. I don't think we need to do that. I can now at this stage. Let me see if I can't get this to transpose vertically so I can copy it into SPSS. SPSS will actually calculate this. Paste special, and I need to. Where is it? Column widths, validation, transpose. Maybe I got to do this. Cancel. 1, 2, 3, 4, 6, 7, 8, 9. Oops. Transpose. It worked. What do you know? Okay, so I'm going to take this. I'm going to copy this. And I started SPSS 2 hours ago because I knew it would take time for it to start. So hopefully it'll just open up now. Oh, it's a miracle. Okay, I'm going to say new data file. Oh, look at that. It's just blazing now. Maybe that's really the trick. You need to start it up and that's to load everything in memory or something like that. Okay, so I pasted in those values. I'm going to go into, I'm going to rename that variable salary. Okay, and I'm going to make sure it realizes that it's a scalar value. Okay, so I'm going to check to see, I'm going to do the same calculation using SPSS. We really should do that too, because there's likely to be problems on the exam that are going to use SPSS as well. So I'm going to say analyze, compare means, right? We're past the descriptive statistics stuff. Compare means. This is a one sample t-test. We only took one sample. We're comparing it to a specific number. One sample t-test. So we're testing the variable salary, easy since it's the only one there, and we're comparing it to the number 350, right? So I'm going to go ahead and in options you can tell it what confidence interval you want, what your alpha is. In our case, alpha, our level of error that we're willing to accept is 5%. So confidence interval is 95%. If we wanted to be 99, if we wanted our alpha error to be 1%, only one chance of being wrong, if we reject the null hypothesis, we change this to 99%. Okay, but I'll leave it at 95%, and I'll click OK to do the calculation. It'll calculate the t-score just as we did before. Maybe. I'll give it another. Oh, there we go. Okay. It calculated the t-score just as we. Oops. Okay. Just as we did before. Calculate t-score. Drag it up here. T-score. Our standard deviation for the sample. Our mean for the sample was 337.78. Standard deviation 13.94. Just as we calculated it. 4.6 roughly was our standard error. Our t-score turned out to be minus 2.63, just as we calculated. Now, in this case, though, SPSS, since it has an infinite t-table in it, rather than just some values of t-scores, it actually calculated the probability of being wrong if we reject the null hypothesis. Another way of looking at it is the probability of getting this big a t-score, this big a difference, if the salaries of those employees really were 350. what's the probability of that occurring? Probability of that occurring is only 3%. Since it's less than our tolerable level of error, which is alpha or 5%, we reject the null hypothesis and accept the alternative hypothesis. Except that SPSS did this for us. Now, it also calculated a confidence interval for the difference between our average and the average salary. And you notice it says, the difference between our sample population and the real population suggests that we're 95% sure that the difference between these two groups is between $1.50 to $23 in salary less for this group we sampled, for the population that we sampled, right? So since the difference is 95, and since 0 is outside of the confidence interval, that's the same as having a t-score that allows us to reject the null hypothesis, right? If the null hypothesis were true, the difference would include 0, right? In that confidence interval. Okay. Okay, so let's see what we need to look at next. Now, what's the next step? How about a t-score where we're dealing with 2 samples, right? When we're dealing with 2 samples, we use a 2-sample t-test. Okay, and we have a little bit of a complication there when we deal with a 2-sample t-test. I'm going to use an existing, since I don't want to spend too much time on this, because I think mostly you'll wind up using SPSS for this. Okay, so with a 2-sample t-test, let me see if I got it. Okay, I have a few data sets that are on Blackboard that I've already opened up here. Kids drinking coffee. Okay, I don't remember the exact background for this, but the 2 variables here are whether or not kids drink coffee. So we have 1, they drink coffee, 2, they don't drink coffee. And the other variable is a numerical variable. See, it's scalar. Is a numerical variable called pacer laps, and maybe that's the number of laps that they can run on the track or something like that. We want to see if there's a difference. I guess to be honest with you, I don't remember the origin. So maybe, but that's what we want to know. We want to know if the average number of laps that the kids in these 2 groups run is the same or different. Okay, so our null hypothesis would be that the mean number of laps run by kids who drink coffee is equal to the mean number of laps for kids who don't drink coffee. Our alternative hypothesis, again, I'm not making a judgment as to whether, maybe coffee, stimulates them, they run more laps. Maybe, it keeps them awake at night, so the next day, they're tired, so they run fewer laps. I don't know, I'm not going to make a judgment. That's a 2-sided test. When you don't make a judgment as to whether something's going to be greater or smaller, then you're doing a 2-sided test. Mu1 is equal to mu2. The alternative hypothesis, mu1 is not equal to mu2. That's it. Okay, so I'm going to go in here and I'm going to go to Analyze, Descriptive Statistics Explore, just because I want to look at the means first. So I'm going to put into my dependence list what I'm going to calculate the mean for, which is the number of laps that are run. And into the factor list, the whether or not they drink coffee. And the values there, let me see if I can remember what the values were 1 and 2. Yeah, 1 and 2. Okay, I need to know that because in a second, it may ask me about that. So actually it's going to ask me a little bit. Okay, so I'm going to go into statistics here and ask it to do 95% and then plots. Okay, I'm just going to click OK. And it should be working on it any second now. Here we go. Okay, let's see what it calculated. So it calculated that there are 9 kids that drink coffee, 13 kids that don't drink coffee. And the mean for the number of laps for kids that drink coffee is 21. The mean for kids that don't drink coffee is 29. So it looks like it's different. But now we have to decide whether it's different enough for us to reject the null hypothesis. This also calculated confidence intervals, the standard deviation, and so on and so forth for both of these 2 groups separately. And it also calculated box plots. You can see there's a big difference there, right? So remember, box plots, now while we're at it, box plots. These feathers represent the minimum and the maximum level of the people that were not considered outliers. The first bar, the bottom of this center section, that shaded section, is the 25%, the 25th percentile. 25% of the people in this study are below that level. The black bar in the middle represents not the mean, but the median, right? The 50th percentile. Okay, the top bar represents the 75th percentile, and the top feather at the top represents the highest value. So we can see that the kids that did not drink coffee ran more laps than the kids that do drink coffee. Okay. Now the thing I also see here is that this median is in the middle of this box plot for the coffee drinking kids. That suggests that this is a normal distribution, right? Normally distributed. But the bar here for the kids who don't drink coffee is kind of skewed to one side, isn't it? Right? Okay, so that suggests that that this is notice how far away the minimum value is from the mean and from the upper value. That kind of suggests that this is skewed to the low end. In other words, there's some kids that are running very few laps, fewer laps than most of the other kids. So this looks a little bit skewed. Just for the hell of it, I'm going to go back into Analyze. It's doing that to me again. I got to be in order to get that. Descriptive statistics, Explore. This time I'm going to make sure that it gives me a histogram, just to see if that's really true. Let me check in the meantime while we're waiting. How are you guys online doing? Okay, still no comments online. Okay, there we go. Okay, kids who do drink coffee, right? I really shouldn't bother with this, right? It's such a small sample size. I really shouldn't have expected it. But you can see this is pretty evenly distributed. Where this one, there's some kids down at the bottom end that kind of skew this a little bit to the left, right? So that's what we were seeing there with that bar. Okay, so anyway, so let's take a look at the actual calculation. We're going to analyze. We're going to compare means. And this time we're going to do independent samples t-tests. We independently sampled population 1, kids who drink coffee, and population 2, kids who don't drink coffee. So I'm going to use independent samples t-test. I'm going to move the laps into the test variable. I'm going to move coffee drinking into the grouping variable. Now it's going to ask me to define the groups. In other words, to tell it that the number 1, it represents one group, the number 2 represents the other group. So it's handy to remember that. And I'm going to click OK. So now, one of the problems we have here is calculate a mean for one group, calculate a mean for the other group. So we subtract x bar minus top part of the equation where we're calculating the t-score or the z-score, depending on the sample size. X bar 1 minus x bar 2 gives us the difference between the two, divided by the standard error, tells how far apart they are. So is that t-score calculated on that formula, is it big enough to reject the null hypothesis? We got a problem. Well, we only had one sample. It was easy to calculate the standard error because we only had one standard deviation. Only one sample, one standard deviation divided by the square root of n. Now we got 2 samples. Which of the 2 standard deviations do we use? We have to make a decision. We have to make a decision whether or not these 2 standard deviations are equal to one another, or if the 2 standard deviations differ from one another. If they're roughly equal to each other, we might consider adding the 2 of them together and getting a better, more accurate calculation for the standard, for the combined standard deviation or pooled standard deviation to get a better answer. So the question becomes, are the standard deviations the same or are they different? When we use the formula, we got 2 different formulas. If we make the assumption they're the same, we use formula A. If we make the assumption that they're different, we use formula B. Okay, I'll write those formulas for you. Hopefully you won't need to use them, use SPSS. So normally, If they're less than an order of magnitude different, right, we assume that they're the same, right? So in other words, if the standard deviation of group 1 is 7 and group 2 is 9, we say that they're the same. Standard deviation of group 1 is 7 and the group 2 is 20, then we would assume that they're different. SPSS actually does a test to determine whether they're the same or different. Okay, so I'm going to raise this up here, and here's SPSS. Here it did the standard calculations of two standard. Notice how close those standard deviations are. They look like they're the same, right? So we're probably going to wind up pooling these two standard deviations. Okay, and standard error, to calculate the mean, 21 and 29, just as we calculated it. Okay, so let's look at our t-test. Our t-test is over here, see T? But before that, there's a box over here, a 2x2 box. I don't know why I have Facebook open now. Quit Facebook. Let's quit this. So at any rate, how did that come up? I mean, why is this doing this? Okay. Okay, so at any rate, what was that, a baby picture or something like that? What do you post a baby? Yeah, whatever. Okay, so at any rate, this 2x2 box over here, Levine's test for the equality of variances. This is pretty confusing, right? The reason why it's confusing is because you kind of look at the significance and you want to say to yourself, well, maybe I want this to be less than 0.05 so I can use the top line. That's not the way it works. The way it works is just like all the other hypothesis testing that you do, you start with the assumption that they're equal. So if we're looking at the variances, whether they're equal or not, what's our starting assumption? That the variances are equal. In order to reject, we have to have 95% certainty that we're not going to be wrong if we reject. So that means our significance, our p-value, has to be smaller than 0.05. So this significance in this box over here, F statistic and significance, has to be less than 0.05 in order for you to reject the null hypothesis that they're equal and to use the bottom row, that they're not equal. So this means I have to stick with the top row, equal variance is assumed, right? Which matches with what we observed, 5 and 6. They're really close to two variants. So I go across the top row, and it calculates the t-score. How to calculate the t-score? It took the difference between 29 minus 29 is a difference of 8. It divided 8 by the standard error, right, which was standard error, which was 2.53, and it came out with a t-score of negative 3.2. Okay, so now right away, negative 3.2 is a pretty big t-score. What's the probability that I would get that big a t-score, that big a difference in the standard error between these two values if they really came from the same population, if the two means of the populations they came from is the same, and the probability that that would occur is 0.004. It's less than a half of 1%. Since it's less than 5%, we reject the null hypothesis, accept the alternative hypothesis, right? Okay, so this is a two-sided test. If it had been a one-sided test, the way I would have described the null hypothesis is that not mu1 is equal to mu2, but mu1 is equal to or greater than mu2. And the alternative hypothesis would be less than. Okay, or mu1 is equal to or less than mu2, and the alternative would be that x1 is greater than mu2. The key here is that the equality is always in the null hypothesis, is always in the equality, it's always in the null hypothesis, right? You don't say x bar is greater, the null hypothesis x bar is greater than x, x1 is greater than x, mu1 is greater than mu2, and then put the equal sign in the alternative hypothesis. You always put the equal sign in the null hypothesis. Okay, just if somebody puts a gun to your head in the test and forces you to come up with a single-sided null hypothesis. Okay, so that's the way we would calculate this. You could do this by hand. You remember that sheet of formula? I didn't know we had a sheet of formulas. for that, the main difference between the sheet of formulas is whether or not you made the assumption that the standard deviations are the same or are different. Okay, so, but SPSS can be a lot easier ticket to getting this stuff done. Okay, so now let's take a look. There's a couple of quick questions here that involve some interpretation I just want to bring up. Okay, type 1. Now what we're looking at here is if we reject the null hypothesis and we're wrong, that's a really bad thing. That's an alpha or type 1 error. If we fail to reject the null hypothesis, usually because we don't have enough evidence, a big enough sample size, if we fail to reject the null hypothesis and it really is true the two groups are different, that's called a type 2 error, not generally considered as bad, right? So let's see. Patient named Diana was diagnosed with fibromyalgia, long-term symptom body pain, described antidepressants, being skipped she didn't believe that the antidepressant would help her. However, after a couple of months of being on the medication, she decides the antidepressants are working because she feels like her symptoms are getting better. Write a hypothesis for Diane's skeptical position when she started taking the antidepressants. Okay, what's her null hypothesis? Her null hypothesis is that her mood will be the same whether she takes the antidepressants or she doesn't take the antidepressants. What's our alternative hypothesis? That she'll feel different, better or worse if she takes the antidepressants. Okay, so what's a type 1 error in this context? If you predicted that she feels better or worse, right? But she really doesn't. But there really is no difference in her mood. That would be a type 1 error. In other words, you reject the null hypothesis that there's no difference and say, oh, the antidepressants did something. That would be a type 1 error. Would be as if you incorrectly reject the null hypothesis. Null hypothesis was there's no difference whether she takes them or not. Okay, so if you say that there is a difference taking and you're wrong, right? That's a type 1 error, right? That's what you're saying there is the drug did something when it really didn't make any change. Okay, and what's a type 2 error? Type 2 error is if you say that you don't reject the null hypothesis when in fact her mood is better or worse after she takes the antidepressant. Okay, that would be a type 2 error where you could have rejected the null hypothesis or should have, but didn't have enough evidence to go ahead and do it. That would be a type 2 error. That's not so bad because in that case, remember, you're not saying that the drug didn't work. You're saying that you didn't have enough evidence to reject the null hypothesis. You failed to reject the null hypothesis. You're not really choosing an incorrect statement, right? You just failed to reject it. You didn't have the evidence to reject it. Right? So type 1 errors are bad because there you're saying, nope, that the drug worked. Type 2 errors, well, I didn't have enough evidence to say to reject the idea that they didn't work. Not quite so bad. Okay, formula for t-test. Following formula is used to determine the t-value for which type of test. Well, we got two means here, x bar and y bar, right? You could x1 bar, y2 bar. So what is this? This is independent samples, right? And in this case, we have x2, x standard deviation for the x group plus the standard deviation for the y group over their individual sample sizes divided by this is how they calculated standard error. If you look back at your formula page, which of these would be the situation where you would use this? Is it a single sample test? No. Is it a paired samples test? No, because we'd be looking at the differences, not the individual difference. In other words, we would be looking at the mean difference is not minus 0 or something like that. Okay, so it's not a paired samples test. It's an independent samples t-test, x and y, and with equal variances or with unequal variances. I'll answer this one for you since you don't have formulas in front of you, but it's with unequal variances. This is the formula that you would use for standard error with unequal variances. Okay, so just so you know, we'll make up like I said, we'll make up a sheet for ourselves so we're ready for it and so on. Okay, so let's take a look at the next step. The next step is when you're looking at 3 or more means or point estimates that you want to compare. Okay, and that's where we're looking for analysis of variance. Okay, so let's take a look at analysis of variance, and I think save changes. I don't want to do that. Let's see what I have here that has more than 2 variables. Okay, so I'm going to go here to math performance by major. Okay, we have 3 majors: education, business majors, behavioral science. We have 4 fine arts majors. And these are their performance on some sort of standardized exam. So I'm just gonna go up here to analyze, just for the hell of it, and say explore, and I'm gonna look at what the average score is factored by major. And let's click OK, just to see the difference. The only thing about this here is I'm not letting you guys do this on your own. So you really need to sit down with maybe some of these examples and work on your own, or go back over some homework problems or quiz problems, and let me know which ones you have problems doing, so that you guys, so that it works better if you guys get on the bicycle and pedal yourselves. Okay, so it's kind of hard to do when with such a limited amount of time. So okay, so the output came up here. So let's see, there's 4 groups. Education majors had a mean of 56, business majors 74, behavioral science majors 55, and fine arts majors 48. Maybe it's a math test, right? Fine art majors didn't quite do quite as well. Okay, so we want to see, we know that they're not the same. We wouldn't expect the population to be the same, but we want to see if we can say with 95% certainty any of these are different. Now we could use a t-test, compare education majors to business majors, and education majors to behavioral science majors, education majors to fine arts majors, and then business majors to fine arts majors, et cetera, all the permutations, right? But that's not very efficient, number one, and there's a lot of other reasons for avoiding that as well, such as increasing the amount of error that you're likely to introduce by repeatedly doing a t-test. So instead, we're going to go over to compare means, one-way analysis of variance. Okay, and our dependence list is going to be what we're going to find the mean of, which is going to be our math score. Oh, it is math score. And major is going to go into the factor. Now, it's not going to ask me what are the values for the math score, because it's going to analyze them all. It's not going to just want to compare 2. Right, so I'm going to go ahead and say OK, and run this and see if our analysis of variance gives us a value that's big enough to reject the null hypothesis that mu1 is equal to mu2 is equal to mu3. So here's our bar chart. I did a lot of overlap between these, right? It looks like this one looks different than business majors, look significantly different than fine arts majors. But, even there's some overlap. These others, there's really quite a bit of overlap. So that might be a little bit tougher. So let's take a look at this. It found that, let's see, the F score, the analysis of variance, the value for the statistic, is 3.6. And for this particular sample, these particular sample sizes, for these various groups, the probability of being wrong, if you reject the null hypothesis, which is mu1 equals mu2 equals mu3, is equal to 0.025, right, which is less than 5%. So you reject the null hypothesis. Now the problem is, which of these can we say with any certainty are different from one another? That's when we go back and run the post-hoc test. Compare means, one-way analysis of variance. This time I go into post-hoc, and I think on the test they'll probably tell you which one to use if it comes up. So I'm just going to say Bonferroni, and I'll click continue. And now we're going to get a comparison for each pairing that we might possibly get, kind of almost like the t-test that we would have ran earlier. Okay, as soon as it comes up, and let's see which of these we can say are different. Education and business major. No, we don't have significant. It's not significant enough the difference for us to say, to reject the null hypothesis that the mean for education majors is equal to the mean for business majors. Not big enough difference. Not big enough difference. Not big. 16%. Not big enough difference. How about this one? Behavioral science and business management. 0.165. No. still greater than 5%. The only place where we see an outcome where it's less than 5% is when we compare fine arts majors to business majors. And then we get a result of 2.3%. So that's the only one we can say with less than 5% chance of being wrong, that there's a difference in the mean score for fine arts majors and business majors. You'll notice that you get the same result when you compare business majors and fine arts majors as you do when you compare fine arts majors and business majors. Right? But the results are the same. They just do every permutation for each one of these values. Okay, so that's where we stand there. So that's our analysis of variance. The next thing we might look at now is we've looked at just about every way that we might analyze point results. So now the next thing we might come across is chi-square and contingency tables. Categorical variable, when we have more than one categorical variable, instead of a categorical variable like major and a numerical variable like test score. Right now they're both categorical variables like diabetes status and gender, let's say, something like that. So we'll look at that on Wednesday night. Let's call it a night. And by all means, send me examples where you're having issues and stuff like that. Go through that list and go back and look at the quizzes that you did as the semester went on. I would also kind of prepare over the weekend, maybe go through all the old PowerPoints just to see, because you'll have access to that stuff. But if you read through the PowerPoints, even if you don't remember something specific on the PowerPoint, you'll be able to go back to the PowerPoint and you'll be able to get to what you need quicker than if, you don't take a look at it and get familiar with it again. Okay, so I would go through all the PowerPoints, all of our PowerPoints again, maybe, take a glance through the homeworks and the quizzes and see if there's some examples that you struggled with or that you don't remember. Because then on Wednesday, I'm gonna start with chi-square. I'm going to go through chi-square, and I'm going to go through at least linear and multiple regression. I'm going to talk to her about and find out whether or not logistic regression really likely to be on the test, but at least linear and multiple regression. So we can cover that chi-square and odds ratio on Wednesday night. But then also, I hope maybe we can get into some of your examples. And then on Sunday, we'll concentrate on stuff that you really think that you need some help on.
Is it Sunday or Saturday?
Saturday, I'm sorry, whatever day. What's that?
They be recorded.
Yes, yep. And this one I actually remembered to record also.